We are now going to study a theorem which is of central importance in fluid mechanics and deals with the kind of energy that is possessed by a moving fluid and how this energy level changes as the fluid moves from one point to the other. It is known as Bernoulli's theorem after its discoverer, Bernoulli, who was a famous mathematician and physicist. And he discovered an important insight into the behavior of fluid in terms of the energy that it possesses due to its position or location or velocity. So let's delve deeper into this through this example. So here we have a pipe which has a varying cross section. So we have the fluid entering at a height of h2 and exiting this pipe at a height of h1. The fluid has different velocities as it travels through these points. It also has different pressures. So we have pressure P2 at point E for the aperture or area A2, and we have pressure P1 at point B for the aperture or area A1. Now, if we were to calculate the amount of work being done at both of these points, we could come up with different results because there is a change within the energy of the fluid as it moves from one point in this pipe to the other. Let's calculate what this change is. So, at point A1, the work done in moving the fluid can be given as P1 multiplied by A1 multiplied by V1 delta T, where P1 is the pressure at point A at the region A1, A1 is the magnitude of the area, V1 is the velocity of the fluid, and delta T is an infinitesimally small amount of time. So we can abbreviate this as P1 multiplied by delta capital V, where delta V is the change in the volume of the fluid moving through this region. In the same way, we can also calculate W2, that is equal to P2 A2 V2 delta T, or we can write this as P2 delta V, where all the symbols have the same meaning. Now, the work done or the difference between the energies between these 2 points in the fluid tells us the work done in moving the fluid from one point to the other. So we can find the difference in work done as W1 minus W2 is equal to P1 minus P2 delta V. Now, the total amount of work done does not tell us how this work is being converted inside the fluid. Some part of this energy will be used in changing the kinetic energy of the fluid. Some part of it will be used in changing the potential energy of this fluid. So we have to treat these two terms separately. So let's do that. So delta U, that is the change in the gravitational potential energy of the system, is equal to rho multiplied by G multiplied by delta V H2 minus H1, where H2 minus H1 is the change in the height since we are dealing with gravitational potential energy. Delta V is the change in volume, rho is the density of the fluid, and G is acceleration due to gravity. On the other hand, the change in kinetic energy, that is delta K, can be expressed as half rho delta V V2 square minus V1 square, where delta V capital is the change in volume, V2 square minus V1 square is the square of the change in velocity, while the change in kinetic energy, that is delta K, can be written as half rho delta V, that is capital V as in volume, bracket V2 square minus V1 square. These are the squares of the change in velocity between the points 1 and 2, and this gives us the total potential energy and kinetic energy of this system due to the change in the position of that particular parcel of water which is moving through this pipe. We can combine these two equations to find out a consolidated equation that gives us P1 plus half rho V1 square plus rho GH1 is equal to P2 plus half rho V2 square plus rho GH2. So this equation, which tells us that the sum of the pressure energy, potential energy and kinetic energies of the fluid remain the same at all points within the flow, is what we know as Bernoulli's theorem. So Bernoulli has in essence restated the law of conservation of energy for a specific class of fluids. Now we have to remember that this analysis requires many simplifying assumptions. For example, we are considering the flow of the fluid to be perfectly inviscid or non-viscous. There is no friction within the molecules of the fluid. There is no interaction between the streamlines in the fluid. So all of the energy of the fluid is being used in either kinetic energy or potential energy or gravitational potential. There is no loss of energy due to friction, no dissipation of energy in the form of heat within this system. But even with this assumption, this is a very powerful result because it gives us an insight into how fluids behave when their pressure and velocities change. There is an interesting application of this theorem, that is in the functioning of aircraft. For example, if you closely look at the cross section of an aircraft's wing, you will notice that the wing is curved on the upper side and flat on the lower side. The reason for this is, as the air accelerates over the wing, its speed is increasing here while the speed remains constant below the wing. If you look at Bernoulli's equation, you will realize that any one form of energy can only increase if another form of energy within the flow is decreasing. If the kinetic energy of the airflow over the wing is increasing, then its pressure energy will decrease. So consequently, due to the acceleration of the air over the wing, the pressure exerted by the fluid on the wing will decrease. This imbalance in pressure between the upper surface of the wing and the lower surface of the wing creates a net upward force, and this upward force is what we know as lift. So this is an example where Bernoulli's theorem is able to explain the functioning of the wings of an aircraft.
Manorama Horizon. Learning made simple.